Hi everyone, this video is an exercise 12 by question 5. So in this question, we want to show that the stationary point of this curve is a point of inflection. So in order to show that the stationary point is a point of inflection, we need to find the stationary point, and then by having the second derivative, we need to check the behavior of the function just before and after the x coordinate of the stationary point. And if there is a change of sign, then that means we have a point of inflection. But before that, let's show all the steps. So we first find the first derivative as usual because we want to find the stationary point. So we get 3x squared minus 6x plus 3. Now we solve the equation, divide by dx is equal to 0. So we have 3x squared minus 6x plus 3 is equal to 0. And we can take a factor of 3 here. So we have x squared minus 2x plus 1 is equal to 0. And then inside the bracket, we can first divide both sides by 3 to just, get rid of the 3. And then this expression is just an identity because this is equal to x minus 1 squared is equal to 0. So this means the solution to this equation is just simply 1. X is equal to 1. So 1 is the x coordinate of the stationary point. To find the y coordinate, we just substitute 1 into the equation. So when x is equal to 1, then y is equal to 1. So now we have the coordinates here. So we have the coordinates of the stationary point. And now we want to determine that it's a point of inflection. But first, we need to find the second derivative. So the second derivative is equal to 6x minus 6. Okay. Now we solve this equation. We substitute the x coordinate of the stationary point into the second derivative, because in the usual cases when we get a maximum or minimum, we normally, if we have a maximum, then when we substitute the x coordinates of the stationary point, we get a negative number, and if it's a minimum, we get a positive number. So in this case, let's substitute and see what happens. We know that it's going to be a point of inflection, but imagine that the question basically hadn't given us that. So when x is equal to 1, then the second derivative becomes, 6 minus 6, which is 0. And always remember that if you get 0 for the second derivative, then you need to check if it's a point of inflection. So in this case, that's why we are going to check if it's a point of inflection, because the second derivative is 0 when we substitute 1. And in order to check if it's a point of inflection, all we need to do is simply considering 2 points. So a point should be just before 1 and the other one should be just after 1. So we can take, let's say, x1 as 0.9 and also x2 as 1.1. So as you can see, these 2 points are very close to 1. And then check the sign of the second derivative at each of these points. So when x is equal to 0.9 and we plug that into the second derivative equation, we are going to get a negative number. And then when we have 1.1, after substitution, we get a positive number. And as you can see, we have a change of sign. And that's exactly what we want to get if we want to show that it's a point of inflection. So if there is a change of sign when you substitute 2 values in the second derivative, then they indicate that the point here, 1, 1, is a point of inflection. So since there is a change of sign, this point is a point of inflection. Okay. And there's another part to this question which says sketch the graph of y is equal to x cubed minus 3x squared plus 3x. So we need to use the information from the question to sketch this graph, because we have the basically the y-intercept is obviously 0. Then the other useful thing about this graph is that it's obviously the coefficient of x cubed is positive. Then the next thing is that this has a repeated root at 0. So that's the only root to this equation and the only x-intercept. And finally, the last thing that is going to help us for sketching is the solution, right? I mean, the point of inflection, because 1, 1 is a stationary point, which let's say is here. So yeah, roughly here. So this is the point of, let's, yes, just plot that point here, for example, because that was too close to the y-axis. Okay, so this is the point 1, 1. I will write like this. And this is a stationary point. So this is where, because we know that this curve is positive, so that means it's a cubic, so it's going to start like this. But since this is the stationary point, it changes the direction, but it's important to know where it's going to go. And you need to remember that this stationary point is also a point of inflection. And at a point of inflection, remember that the curve changes its concavity. So you will learn about these terms in PO2, but remember that if a curve is concave, then it has this, sorry, it has this form, and then if it's convex, it has this form. So for positive is this, for negative is this. So in this case, remember that we found that when x is 1.1 or greater than 1, the curve, the second derivative is positive. So that means the curve is convex, which means it's going to have this sort of direction, which as you expected. And then after that, since we get a negative second derivative, that means the curve becomes concave. So it's going down. And obviously, this is the x-intercept, and it just keeps going. So this is roughly, this is the rough sketch of the graph. And yeah, so that's it for this video, and thank you for watching.